Okay, let's get started. So let me introduce our keynote speaker, Irina Calciu. She is a co-founder at Graft, a cloud-native startup that makes the AI of the 1% accessible to the 99%. Irina is broadly interested in machine learning systems as well as parallel and distributed systems with a focus in algorithms and systems for rack scale computing. Before Graft, Irina was a senior researcher at the VMware Research, working on novel software hardware co-design solutions for memory disaggregation. Irina completed her PhD at Brown University, and Brown University, and then worked for the algorithms for non-uniform memory access architectures and hybrid transactional memory. Irina has co-authored papers at top conferences, obtaining best paper awards at ASCLD and Transact. Okay, let's get started.
Great, thank you for the introduction. Hello, everybody. My name is Irina Calciu, and today I'll take you on a trip down memory lane. And by that, I mean heterogeneous and disaggregated memory lane. A little about myself. Yes, I'm a Graft co-founder. I've been a co-founder for almost the past 2 years, I'd say now. Graft is a machine learning startup, and I'll talk a little bit more about that in a minute. And before that, I was a researcher at VMware Research, and a lot of the work that I'm going to talk about today actually is from that time. And I did my PhD at Brown. And if you want to contact me, this is the best email to reach me. So about Graft, yeah, we are a cloud native startup, and our aim is to be the foundation for modern AI. We empower organizations to use all of their data and get insights from that data. And this is all unstructured data that these organizations have, such as text, images, video, audio, graphs. The nice thing is you don't need to have a machine learning team that needs to access Graft and get insights from the data. We can do this very easily, even without any kind of machine learning team, machine learning infrastructure, or machine learning expertise. And since we're talking about machine learning, let's look a little bit at modern applications. And a lot of these applications are machine learning applications. In general, they are complex distributed systems, and they require a lot of memory in order to perform their operations. And there are several reasons for this. First, they have to ingest large data volumes. Oftentimes, we nowadays deal with large models, and training these large models takes a lot of resources. It's very time intensive, data intensive, but also in terms of the infrastructure, they require a lot of infrastructure resources. And of course, the cost for this ends up being pretty high. And even after we've trained these models, there are obvious reasons why we want to continue pre-training the models as well as fine-tuning them. Eventually, you want to compute representations of the data, as well as index it and make it easily accessible and searchable. And a lot of people, a lot of users want real time most of the time, but they want pipelines for recommendations, for predictions, for data insights. So all of these operations and all of these applications require large amounts of memory. And oftentimes, it's not sufficient to just provision the amount of memory that we need, the exact amount of memory, even if we were able to predict that, which is very hard. But we have to provision extra memory just to make sure that at the peak, we don't run out of memory and we don't cause out of memory issues, and our applications don't die. So I'm just included on the slide one example for ChatGPT, since it has been in the news a lot. And it seems like people are estimating that it costs them about $3 million per month just to operate ChatGPT. This doesn't include any of the training costs. So that's a huge amount of money. And significant chunk of that is the cost for memory allocations in order to provision the infrastructure for this. Now, what happens is that cloud infrastructure is pretty good. There's a lot of memory available, and there are a lot of instances nowadays in the cloud that are available with large amounts of memory. So you can go to any of the major clouds and then provision instances of 18 terabytes, 24 terabytes of memory. That's a lot of memory on a single server. Unfortunately, if you look at the costs, these costs are also proportional to the amount of memory that you require. So if you need smaller instances, then it's actually pretty cheap to run stuff in the cloud. But if as you get to the high-end bits where you have a lot of this memory being provisioned, it gets more and more expensive. And these costs, as you can see, the difference in these tables, they're actually quite significant as you get into the high-end, high memory instances. So not only that, but all of these servers today are not uniform memory and single type of memory anymore. Most of the time, servers are non-uniform memory access machines. So that means accessing memory locally from one CPU takes less time than accessing the memory of another NUMA node. And this is not even exposed to applications. It's actually pretty transparent. It all looks like shared memory, but in reality, the costs are different. And this adds complexity in writing these applications. And of course, there's a lot of exciting developments going on in the memory space. So NUMA is something that we've dealt with for years now, but new memory technologies are emerging. So there's persistent memory, high bandwidth memory, and now CXL is going to open up a whole new opportunity to have new types of memories attached, as well as new interactions that applications have with this memory. And it's not just the memory, but it's all of the resources that are in data centers today are pretty heterogeneous. We don't run compute on CPUs anymore, but they span a large number of accelerators and GPUs or FPGAs, TPUs, and all of this hardware diversity is increasing. And as I mentioned, CXL makes it more possible that we're heading in the direction of disaggregated memory, disaggregated everything. In fact, we can have pool of these resources as well as pools of memory that are physically disaggregated from the traditional server box. And this is a very exciting future to be talking about, because memory disaggregation or resource disaggregation in general enables not just cost savings, but a lot of exciting opportunities to look forward to how to define our infrastructure going forward. So for this talk, I will mostly focus on discussing remote and disaggregated memory, and I'll talk about one taxonomy for remote and disaggregated memory, and then discuss a bunch of things related to this, such as the benefits and trade-offs that we get, new programming models for it, as well as how to obtain disaggregated memory or remote memory today using application changes, virtual memory, which is a mechanism that has been often used in this context, as well as memory or cache coherence, which is a new approach that we proposed recently. And then a little bit towards the last part of the talk, I'll get into programming models in general for heterogeneous memory. So if we're talking about disaggregated memory, let's talk about why do we want disaggregated memory? Why is this important? As I said, there's a lot of over provisioning going on in data centers, which means memory is underutilized. So by some estimates, memory utilization is at about 60 or 65%. And this is really low because memory is a very expensive resource, which means we want to be able to make the best use of it. And with memory disaggregation, we'd be able to not only decrease the memory over provisioning on each host by having these pools of memory, but also improve utilization of the memory that is available and distribute the allocation of memory according to what applications actually need, as well as make it more dynamic for applications to request memory. It doesn't have to be tied to the box, to the physical box. Therefore, we can virtualize the allocation of this expensive resource. It's also beneficial for enabling access to remote accelerators, as well as from a cost perspective. It generally improves costs in data centers for infrastructure provisioning, as it allows us to decouple scaling of memory and compute as we buy different resources. It also decouples failures because, again, we're not tied to a physical box anymore. Therefore, if a particular resource fails, we can just replace that resource or just reallocate and reroute the data or an application to use a different resource. Of course, this is not really a new idea, and some of these ideas actually are quite old. Distributed shared memory is a related idea, or swapping to remote memory and file systems for remote memory have been proposed a while ago, as well as the HPC community has been looking at partition, global address spaces, and all of these ideas have seen a recent resurgence in recent years because it's so timely with the need for rethinking how we provision our infrastructure in data centers today. So it's interesting to see the adoption of these ideas in a very different context, as well as looking at how the networks have evolved in recent years in data centers. We see why it's becoming possible to even consider these ideas in this new context. And of course, there have been some systems that proposed modifying applications in order to be able to support this as well. And across all of these systems, the goal is generally the same. We want to be able to pull remote memory either at the software or hardware level, but the mechanisms behind each of these approaches are different. So based on these different mechanisms, I'm going to talk about one taxonomy for remote and disaggregated memory. And this taxonomy comes really from from looking at the stack and observing that there's a semantic gap between applications and remote memory, wherever this runs. It could run at the runtime level, it could run at the operating system level, or it could run even at the hypervisor level, right? But either way, there's a semantic gap between the application's intent of accessing memory and access patterns, as well as what the remote memory knows in terms of accessing which memory we want to access, which pages, or which objects. And different mechanisms have bridged the semantic gap in different ways. So the most common mechanism, I'll say, is virtual memory. And of course, this is one way to bridge the gap by introducing page faults. And I'll talk about this in more detail. Another approach to bridging the semantic gap is to simply communicate what is the intent of the application to the runtime or the operating system that is providing the service of remote memory. And honestly, so far has been more like at the runtime level if you need that application intent, but it really doesn't have to be. And the third mechanism, a more recently proposed mechanism, is to look at cache coherence in order to detect what the application wants to access in terms of this data that is situated somewhere else. And looking at cache coherence allows us to inform the software from a hardware mechanism at a smaller granularity than we would have done with, say, virtual memory. So looking at each one of these individually, let's start with virtual memory. A lot of the systems proposed for accessing remote or disaggregated memory use virtual memory. And the setup for this is that we have an application host where the application is actually running, and there might be some local memory, and this is oftentimes used for caching the remote data. And I don't think this local memory is going to go away anytime soon, even when we have real pools of disaggregated memory. And this is connected through a fast network to a memory host that is remote. And there are several ways in which this can manifest. It could be that this memory host is a symmetric host that's running more applications, but more likely it's going to be an explicit memory host that has large pools of memory available, just making them available to other applications running on the application host. And in order to access pages in this exposed remote memory, the local application is going to map these pages in its local cache. And then whenever they need to be accessed, the remote memory system underneath will fetch these pages on demand when the application uses them. Obviously, if they get to be too many pages, the ones that are not used will be evicted. And in order to maintain the data consistency, we need to track what pages have been modified, and this is called dirty data tracking. And then rewrite these modifications back to the owner of the data, which is the remote memory host. And if you notice here, even though the network is pretty fast, it still might take in the order of microseconds in order to do these accesses, while this local cache is actually in the order of nanoseconds. In order to track dirty data, of course, we again use virtual memory. And in order to do so, there are two operations. First, we need to write protect the pages, as well as whenever the application wants to change something, we get a page fault, and then this page is marked dirty. So here I'm abstracting away particular systems, but I'm showing a graph that shows most of the system's behavior, especially when we have a random access workload. It seems like there's a significant drop when we start putting even a smaller amount of memory into remote memory. And this drop comes from several inefficiencies, but especially the semantic gap between the application and the remote memory system, not knowing what the application intent is and which pages it's trying to access or modify. And it needs to rely on a pretty heavyweight mechanism. There are other overheads, particularly dirty data amplification, because we always work with the page granularity in these cases. So either 4 kilobytes, 2 megabytes, or 1 gigabyte. And we see that for various applications, this has a large impact on the amplification that we get between what the application actually accesses and how much bandwidth we need to provision in order to transfer this data across from remote memory. So for a Redis application that has 2 access patterns, sequential and random, we see that this amplification, even for 4 kilobytes pages, can be between 3 times more or 30 times more. And here I'm just showing visually how much of this page is actually written to versus having to access the entire page. So you can see that the amplification is quite significant. And it gets even worse for large pages. In contrast, if you look at 64 bytes cache lines, this amplification is actually not too bad because it's a much smaller granularity. So we actually access what or modify what we actually access. Now, because of the page faults and write page faults, which sometimes can be quite expensive, we also see some applications slow down. And there's also the cost of write protecting pages, although this is relatively smaller than the other costs. Moving on to the next mechanism, we could just modify applications, and then we don't need to have any kind of page faults in order to inform the system what pages is trying to access or what object is trying to access. And the big advantage here is that we're not restricted to page level access, and this notification can be at an object level. And an object level is really the ideal case scenario because it's the semantic knowledge of what the application is trying to do. And it's a much smaller granularity. If the application is accessing an object that is only half a cache line long, then this is the exact notification that we would get. I'm not sure that it's that there's still some amplification, right? Because if it's half a cache line, then we might still decide to fetch the entire cache line for obvious reasons. But this amplification can be significantly reduced compared to virtual memory that has only page granularity. Now, the downside is that most of the time the application or the library developer needs to be aware of remote memory, and it requires a different programming model altogether in order to be able to support applications. It's usually new applications that get developed in this way. And it's often not applicable to existing large applications, which could take a long time to modify in order to be able to support remote memory with this model. So a third mechanism is to look at hardware support for detecting these accesses from applications and informing the software directly from this new hardware. And in order to understand this cache coherence-based mechanism, let's look at how CPUs access memory. When you're trying to access something, first you bring a cache line into the CPU caches, and there's a protocol based on MESI protocol with modified, exclusive, shared, or invalid states for the cache line. And of course, if there's a read, this cache line will go from invalid to shared or exclusive mode, as well as if there's a write, then we will transition the cache line into modified state. And eventually, this protocol requires that we flush the cache line back to memory. Whether it was dirty, then it's known that we need to write back the data to memory so that we don't lose the new update that has been done. So this seems to be a perfect mechanism to inform at a smaller granularity of what data the application has been either accessing or modifying. And the idea here is to use an FPGA that has memory attached to it, and it is attached to the CPU through a coherent interconnect. Potentially, the CPU might have its local memory, again, close up DRAM that it uses mostly as a cache, and put all the data into this FPGA memory, which means the CPU will have to go through the FPGA in order to access various parts of the data. And when this happens, it will fetch a cache line from the FPGA memory into the CPU cache, put it in shared state or exclusive state. And if it modifies this cache line, it has to, again, send it back to memory so that the data doesn't get lost, which provides the FPGA with the ability to track which cache lines are being accessed, as well as interpose on those accesses. And it provides it the ability to track which cache lines are being modified and keep track of what is the dirty data at the smaller granularity. And there are multiple protocols that provide this coherent interconnect between CPUs and FPGAs. The traditional way to do that has been UPI, but with CXL, of course, this becomes much easier to do without proprietary protocols. So in order to use this idea for remote memory, let's look at it in context, in the context that we were talking about before, that of an application host that is running an application, again, on the CPU, and it has this FPGA connected through a coherent interconnect, as well as a memory host that offers remote memory to these application hosts. And we use this FPGA memory now as the DRAM cache for remote memory. So what this means is that the FPGA becomes responsible for managing this cache and evicting pages back to remote memory when that needs to happen. And dirty data tracking happens transparently whenever there is a modification to the cache line. And it can be transparently evicted and written back to the owner of this memory, to the memory host. As well as we can do demand paging because we can anticipate from the FPGA what are the accesses requested by the application. And in order to do that, we have to declare kind of a fake physical address space that is much larger than this memory. And the CPU ends up accessing data into this address space notifying the FPGA of what is this data that it needs to access. And the FPGA can actually fetch on demand the data that is needed. And of course, this would happen transparently to the application. So it doesn't need to declare whether the access is being made. The benefits are that we can reduce the page faults as well as the write page faults that are necessary in the application. We definitely don't need to do that in order just to track what are the remote memory accesses. And we can again talk about smaller latencies in accessing this data, as opposed to having to wait microseconds in order to get the data on demand with the previous mechanisms. It also significantly reduces dirty data amplification because it works at this much smaller granularity in terms of cache lines, and it can improve network bandwidth because of that. It allows us to also determine access pattern and evolve to other use cases or do smart prefetching just by looking at the small granularity accesses and trying to predict what are going to be the accesses that are going to happen in the future, and then prefetch the specific cache lines or even at the higher granularity specific pages that will be needed in the future. Of course, the FPGA itself will operate at a slower frequency than the CPU, and accessing this memory will be slower. The latency is also a big unknown so far as to whether we'll be able to match the nanosecond latencies or really approach the nanosecond latencies compared to the local caches on the CPUs. By local caches, I mean local DRAM cache, not the actual hardware caches. So there are several primitives that we would need to be able to expose from the FPGA in order to achieve this. The main one is to be able to read and write track using this cache coherence protocol. And here we have several options. We can put data pages into the FPGA memory and track data the way that I've explained so far, but we can also put other special pages and interact with the system at a lower level. So for example, OS pages such as page tables allow us to predict the access before the application requests a particular data page access by just looking at the translation information for the page before the actual access. And the FPGA can just fetch the data beforehand from remote memory. We can also add code pages into the FPGA memory, and that opens up the door to new use cases in order to track various application behaviors. The other primitive is local and remote copy. So being able to locally copy data as well as remotely copying data between the application host and the memory host. And in-place transform allows data changes without actually having to copy the data at all. So it could be encrypted on the spot, for example. And this is the paper where we described the idea on these FPGA primitives and basically emulating in software these primitives and evaluating what their performance might look like if we built a real system. And if we support pages that are not necessarily data pages, then we can enable other use cases as well. So some examples include live migration of virtual machines. This requires both data and page tables to be added to the FPGA memory, as well as in terms of the primitive, it requires read-write tracking and remote copy. We can also do more fine-grained copy on write. So copy on write operates at the page level, causing the same types of amplification that we've seen with remote memory. But we could do a cache line granularity copy on write, for example. Compression and encryptions are examples where in-place transform is very useful, because the FPGA can do the compression or encryption on the spot. And the data in memory will never be unencrypted, for example. And there are many places where this is beneficial. For example, if you want to store secrets, you don't want to accidentally be able to read this data, especially when it's written in the memory of another machine remotely, or if the data ends up somehow being swapped to more persistent storage, like persistent memory or actual storage, then you wouldn't accidentally have it in that persistent medium without actually having it encrypted. Checkpoint and replication is another important use case, or we could do near memory compute, where the FPGA does any kind of compute processing on the data, as well as data access patterns could be for detecting smart prefetching, for detecting accesses that are illegal accesses, such as security attacks, row hammer, or cache-based side channel attacks. If we put code pages into the FPGA memory, then this enables even more use cases, such as binary translation or dynamic code rewriting for applications or even for the operating system, tracing and code coverage analysis. So the FPGA could transparently do this analysis without interfering with the application normal execution, and it could do this in almost real time. And the primitives that are needed are, again, retracking or in-place transformation. So this is the paper where we included more details on all of these other use cases. So as I mentioned, this was mostly work that I've done when I was at VMware Research. So I wanted to call out Project Peaberry at VMware, which is an ongoing project. And this is a blog post from VMware CTO talking about this project last year. And it was very exciting to see that the CTO thought that this was one of the highlights of the year for VMware. So that was very promising, as well as he references several of these use cases that I mentioned, such as live virtual machine migration, as well as vMotion operations and remote memory, and some of the others that I mentioned. So to wrap up, the taxonomy that I talked about refers to 3 different mechanisms to obtaining remote memory. One is modifying applications and making these applications aware of remote memory. The second mechanism, the most commonly used in practice today, is virtual memory, so getting page faults in order to access remote memory. And the third mechanism that I talked about is using cache coherence to transparently detect what data is being accessed or what data has been modified, and write that to remote memory. So this slide just summarizes the main details of each one of them. The application needs new programming models. And if we write new applications from scratch, maybe this is a way to go about it, make the application or a particular library aware that it's going to access data in remote memory. It does object level tracking, which could be beneficial because it reduces amplification, and it specifies exactly the granularity of the object that is being accessed, but requires code changes and a lot of awareness regarding the details of the remote memory. Sometimes can go even into the latency considerations as to how far the memory actually is. And the application or library programmer needs to be aware that of this remote memory. Now, virtual memory and many systems use this is at the higher granularity, which causes more amplification and increased network bandwidth, but it's also transparent. So applications don't need to be aware of the data being remote. And finally, memory or cache coherence is a new paradigm based on coherence that, again, doesn't require page faults, so results in faster access. And it's at the cache line granularity, so it uses network bandwidth. In the end, I suspect that what we'll reach a consensus on is that we'll probably need to use ideas from each of these mechanisms, and perhaps combining them will hold not just the best performance, but also the best usability for applications and for developers as well. So what is next for disaggregated and remote memory? We've seen the benefits already, and there are many benefits. So there are good reasons to believe that disaggregated memory is coming, and it's coming soon. And CXL is a very exciting opportunity to enable the adoption of disaggregated memory. So I'm looking forward to seeing more of these developments where CXL is not just on the roadmap, but it's actually adopted in practice, and we see how these remote pools of disaggregated memory perform. And we will have to rethink the memory and cache hierarchy for these new types of memory that are going to be adopted once that is becoming a reality. And I'm also looking forward to seeing what is the latency that we will see in order to access this data. So finally, I just want to talk a little bit more about programming models in general for heterogeneous memory, not just disaggregated memory, but the fact that, as I said before, servers are very heterogeneous and NUMA. So accessing memory, even locally within the same box, is has very different constraints than what the abstraction really leads us to believe, the abstraction of shared memory. So for that reason, I think we need new abstractions in order to be able to properly deal with these new types of heterogeneous memory. So one programming model that we proposed in the past is called node replication. And this looks specifically at data structures. So you take a sequential data structure and you expose certain operations on it, such as create a data structure or execute a mutating operation on the data structure, as well as being able to detect, is this a read-only operation or is it a mutating operation on the data structure? And based on the sequential data structure, we can automatically make it so that it's concurrent and NUMA aware, so that multiple threads running on different NUMA nodes can access this data structure concurrently without actually needing to acquire locks or doing anything more complicated in order to synchronize the access. And this is a promising programming model, not just for NUMA, but in reality, I think it can be promising for a lot of the new types of memory that are emerging, including persistent memory and remote memory or disaggregated memory. And the way this works is, at least for data structure, you just replicate the sequential data structure on each of the NUMA nodes. So each node would have its own local replica. And then there is a shared log that each of these nodes have access to. And this log contains a representation of the mutating operations on the data structure. We don't include read-only operations, just mutating operations. And each of these replicas could be farther along down this log of operations, or could be lagging behind. But in order to do a new operation, what it has to do is allocate some space in the log, write the mutating operation that it's trying to execute, as well as then execute the operation on the local replica after it has been already linearized on the shared log at the particular location in the order. And of course, we can batch multiple operations that come from the same NUMA node, so we don't have to incur the cost of writing each operation individually into the shared log. And this batching is beneficial in order to reduce the synchronization costs. And when a new operation arrives and we want to execute it on a replica that is out of date, then what we need to do is basically update the replica, make sure that it's up to date, and then insert the new operation on that particular replica. But this allows other paradigms as well. We don't have to have exact replicas between the different NUMA nodes, or even between different heterogeneous types of memories. These replicas could each be adapted to the environment in which they're executing. So if we have a particular node with some particular type of memory that is easier to, let's say, access a skip list than a tree, then one of the replica could be a skip list, while the other replica that is in DRAM, and maybe a tree is faster to access, then can be in the form of a tree. It really is not material what type of replication we use, as long as the shared log gives us the truth about the order of the operations that are performed on these data structures. And there are deterministic outcomes to executing these operations. So using this idea of node replication, we realized a new operating system based on node replication. So at the operating system level, you can have the file system or the scheduler or virtual memory all operate in this manner. And there's a log of these operations that tells you the ground truths about each of the data structure involved. And in user space, applications don't need to be aware that this is the case. They can run on each of the NUMA nodes or even across different NUMA nodes and just do system calls into the operating system. Okay, so this brings me to the end of the talk. It's a very exciting time to look at server infrastructure and cloud infrastructure, and to rethink the memory hierarchy and the cache hierarchy for these new types of resources that it's becoming clear that they're more heterogeneous and soon to be disaggregated. So it's a great time to be doing research in this space and really rethinking applications and programming models from the point of view of maximizing the benefits on these new types of infrastructure. So with that, I want to thank you for attending the talk, and I want to thank the many collaborators that have participated in this work that I talked about over the last hour. So thank you very much, and I'm happy to take any questions.
you have any questions, please approach to the left. Your name and can you go your feet to there? Because she cannot hear. Okay.
I have a question about the sequential data structure you presented. Is it some kind of data dependency graph for different coarse-grained tasks?
Can you hear us, Irina?
I think
I
she's
can barely hear you, but it's breaking up enough that I'm not completely following the question.
How
I
about
can
now?
hear.
Can you hear?
Yeah, I can hear you, but I can't hear the question.
Speak louder, please.
So I wonder whether the presented sequential execution data structure is some kind of coarse-grained task level data dependency graph.
It's really a representation of the mutating operations on the data structure. So it's not so much a task graph of the dependencies. It's more the dependencies are really sequential operations. We serialize them completely. They're linearizable data structures, concurrent data structures that result from the operation of putting these in the logs, and it gives us a total order of all the operations. The dependencies are really in this linear order given by the log. Now you can extend this with concurrent operations and put them on several different logs at the same time, and then discuss the dependencies between these operations that some of them might be concurrent, some of them might have dependencies between them. So we also did that, but we did it in a manner that looks at the semantics of the operations, and we try to separate them so that there are no dependencies if you put them on different logs. But in the way that I described it, it's a single log, and that's a linear order between all of the operations.
Thank you.
Yep.
Hello, thank you for your talk. So you made the case for FPGA to track basically cache line granularity writes. If we use typical techniques like directories to basically track these writes of cache blocks that have been sent to other machines or server, then how does it scale? Like how much SRAM resources do you need on this FPGA to track, let's say, some number of blocks?
Yeah, I mean, that's a good question, but it really, it's a trade-off between how much you want to track and how much cache you actually have available, right? So if you don't have that much SRAM available on the FPGA, then you can limit the amount of page tables that you're tracking and track the data directly. So it's really just an optimization that provides you access to that information faster than accessing the data. But in terms of data, you really can do it at different granularities. So you can scale the size of the data that you're tracking in order to fit it into the cache available. So I would kind of repose the question in terms of depending on how much cache we have available, that's how much we'd be able to track.
Okay, thank you.
Yep.
Any further questions? So then let's move on. So thank you so much for Irina. Thank you for a great talk. We're gonna move on to the panel discussion.
Sounds great. Thank you so much for having me. It was a pleasure giving the talk.
Sure.